Hi and welcome to the extended version of my talk on the PARASITE attack. My name is Daniel de Almeida Braga and I'm a PhD student under the supervision of Pierre-Alain Fouque and Mohamed Sabt, working on finding practical attacks on cryptographic implementation in order to highlight weak spots and hopefully make developers more sensitive about some issue that really need to be fixed. The main idea behind my work is to clearly identify new attack vectors and show how practical they may be so that they are considered seriously. So there is often as much work in finding the issue as there is in actually exploiting them, as you may notice during this talk. The particular talk is about our most recent paper, entitled PARASITE for Password Recovery Attack against SRP Implementation in the Wild, which is a work by me and my two supervisors that was accepted at CCS 2021. The goal of this talk is not only to discuss about our paper, but also to outline some properties of PAKES, which make them particularly sensitive to side channel attacks. So I will start by giving a bit of background on PAKES and why we decided to look at them and their implementation before summarizing our actual contributions and dive into some detail of our work. I will end up with the impact analysis of some affected projects and a small discussion on the mitigation of the vulnerability. So first, what's a PAKE and why did we look at them? Sometimes you may want or simply need to be able to establish a secure communication channel only based on the knowledge of a quite short password. This is mainly the case when you don't want to manage a public key infrastructure, or more generally when you want to derive some cryptographic material from the mere knowledge of a password. So that's basically what PAKES for Password Authenticated Key Exchange are for. They are an interactive protocol aiming to combine the key exchange and the authentication parts of a protocol. And the knowledge of the password will be used to authenticate the user, and from this low entropy secret, both parts will end up sharing some strong cryptographic material. Of course, as we are dealing with low entropy password, they have to protect against dictionary attacks, namely offline dictionary attacks. And there are a lot of different PAKES, but we can distinguish two main families. On one side, we have balanced PAKE, where both sides knows the password. On the other side, we have asymmetric PAKES, where there is some clear role of client and server, and only the client will know the password, while the server only know a password derivative value called the verifier. So why did we decide to take a look at PAKES? PAKES are around for quite a long time now, and there are many schemes, but adoption was really slowed down by patents on the first PAKES. And some designs are kind of weird because of the patent's circumvention, making the security proof quite hard. However, recently we've seen a significant speed up of PAKE adoption with two notable facts. First, the choice of Dragonfly to secure WPA3, the new Wi-Fi standards. And second, the recent patent expiration on original design, which triggered a CFRG standardization competition, which ended up quite recently, a couple of years ago. And this recent interest also tickled academics, and we've seen some work assessing their security, both theoretical and practical. We can mention the Dragon Blood attack that made quite some noise a couple of years ago, and more recently the partitioning oracle attack, which applies to some insecure, opaque implementations. In the light of those vulnerabilities, we can't stress enough that side channel leaks are disastrous for PAKE, since they may leak information on a very low entropy value, and each bit may be used independently to halve the set of possible passwords. In this talk, we'll discuss about a particular PAKE named SRP for Secure Remote Password, which is among the most deployed in a lot of contexts. And SRP has been around since 1998 and is the most deployed because it was one of the only PAKE at this time that was not patented, and there was a free open source implementation made available. And there has not been a lot of work on SRP recently, we have seen a few issues that have been outlined, leading to adjustment of the protocol. That's why we're at version 6a, but there is not much recent analysis of the protocol or its implementations. This year at ACNS, we saw a paper showing a side-channel attack based on power analysis on Apple's cryptocurrency library implementation of SRP, which share quite some similarities with our attack. However, we didn't use the same side-channel attack, the target is different, and the practicality of the attack is not the same. So let's say a few words about SRP. First, it's an asymmetric PAKE. So there is really a client and a server roles. The client will know the password, while the server will only know a verifier, which is always the same and is computing once at registration time. An element to notice is that the protocol security relies on the difficulty of solving the discrete logarithm problem on finite fields with some standardized parameters. The protocols go as follows. First, the client will start the exchange by sending their ID and an ephemeral key share to the server, after which the server gets the corresponding information from its database, namely the salt and the verifier, and sends the verifier masked with an ephemeral key share. Once the client gets it, they can compute the verifier, and both sides can end up with the same cryptographic key. So this is the commit step. This step is followed by a more classical verification, where both sides send each other the hashmark of the session transcript authenticated by a key derived from the results of the commit step. One operation you want to be particularly careful with is the computation of j to the power x on the client side, aka the verifier, since here the exponent is deterministically computed from two fixed public values, the ID and the salt, and the secret password. But we'll get back to that point a little bit later. For now, let's sum up our contribution. We reviewed a few SRP implementations that we found to be used in various projects, and we end up noticing that a lot of them relies on the same root library to perform the core arithmetic operation. Namely, they rely on OpenSSL. And by digging up a little bit on the OpenSSL's implementation, we found some leakage in the core implementation of the modular exponentiation that we managed to exploit to perform an offline dictionary attack, allowing to recover the right password in realistic sized dictionary. We also performed an impact analysis on various projects that we found to be vulnerable and developed a full proof of concept on our experimental setup for some of them that we published on our GitLab after the vulnerability has been patched. So let's review our contribution in more details. We have a cache attack that lets us extract information during OpenSSL modular exponentiation, which allows to recover the password with a single measurement. So first, this is a cache-based side-channel attack, which means that we exploit some CPU properties and behavior to leak information on the secrets. In particular, we used a flush and reload attack coupled with a performance degradation attack to come to our end. Before giving some explanation on flush and reload, let's remind that CPU have caches, which are basically very fast access memory they use to store instruction they execute and to store the data that they use to perform the instruction. The use of flush and reload is for the attacker to be able to monitor the calls to some very specific instruction used by the victim. And there is basically two constraints to perform this attack. First, the attacker and the victim needs to share the same CPU caches. And second, the attacker needs to be able to map the address space of the victim process, or at least the part containing the instruction to monitor. To give you a quick example, let's imagine that the attacker wants to monitor the function foo from, let's say, OpenSSL, which is used by the victim. First, the attacker will need to load OpenSSL's library into memory in order to access the same address as the victim for the instruction foo. From this point onward, the address space of OpenSSL library is shared. This means that if either the attacker or the victim load the instruction, meaning execute it, both can see this instruction and can access it in the cache. From there, the attacker only needs to flush the instruction out of the cache. So this is the flush part of the attack. We don't need any privileges to do it. And simply measure how long it takes to reload this instruction, so to execute it. And there we have two possibilities. First, if the victim executed it in the meantime, it is already in the CPU cache, it is already reloaded, so the reload step on the attacker side will be very fast. Otherwise, the attackers need to look for the instruction in higher memory level, which will be slower to access. And this time difference makes the attacker able to know whether or not the victim executed the instruction. So the idea is to loop over this process and track the execution of this particular instruction. Once you get the ID for the flush and reload attack, the performance degradation attack is quite easy because it's basically the first part of the attack, the flush part. The idea is to flush again and again some particular instruction in order to degrade the overall performance of the victim process on this instruction. So the performance degradation attack will not allow us to track the execution per se, but it is more of a tool that we can use to make the measurement easier, to increase the leakage and basically make the overall attack much more accurate. We'll talk a little bit later about how we combine these two attacks. But to come back to our contribution, we observed this leakage during the modular exponentiation of OpenSSL, because a weak algorithm is used when the client computes the verifier. And this leaks some information on a password-related value. With this leakage, we can do a fully offline and completely passive dictionary attack with a single measurement. This last point is quite important in the practical aspect of our attack, because this means that with a single measurement we are accurate enough to get reliable data, thanks to the combination of the flush and reload and performance degradation attack. And more importantly, we can extract enough information to perform a dictionary attack on a very large password dictionary. Now that we have seen and that we know where the problem comes from, let's dig a little bit into the details. As I said, we attacked OpenSSL's modular exponentiation, so let's see how it works. When you are dealing with an odd modulus, which is the case in SRP since the modulus is a large prime, the main function will try to call three different subroutines in the following order. First, if the base is small enough to fit in one processor word and no constant time flag are set, it calls an optimize square and multiply in Montgomery form. Next, if a constant time flag is set, it calls the secure implementation of the Montgomery exponentiation, which include some mitigation to side channel attacks, including the flush and reload attack. However, if none of the above match our case, it calls the classical sliding window exponentiation. Usually, when we hear about attacks on modular exponentiation on OpenSSL, the sliding window exponentiation is targeted. This has been the case for one of the first side channel attack by Percival in 2005, which led to the secure implementation that we have now. But now and then we find some corner case where a flag is not set and it falls back to the sliding window exponentiation, like in a recent Usenix paper that was published last year. Here, it turns out that not only the flag is never set, but SRP fills the requirement for the optimized implementation since the base J is 2, 5, or 19. So I think everyone agrees that using square and multiply itself is an issue, since we can, in theory, distinguish bits to 0 and bits to 1 simply by looking at the operations that are performed. In our case, it's an optimized version where almost all operations are performed on a single processor word W, which makes them really fast and quite hard to distinguish from one another. To give you a better idea of how it works, you can think of this algorithm as those Japanese fountains which fills with water and then pour everything in a bigger recipient when they are full. Here the bigger recipient is our actual result, which will be a big number in OpenSSL sense. And Each bit of the exponent processed will drop 1 or 2 droplets in the accumulator W, which will slowly fill up. Those droplets are very small and close to each other, and we cannot distinguish them in practice with a flush and reload attack. However, when the accumulator is full and we spill the water into the bigger recipient, the operations are significantly heavier and very more noticeable. Now, what's very interesting about this is that for a given word size, so for a given architecture, and a value of j, the base of the exponentiation, the time it takes to fill the accumulator only depends on the number of droplets we pour into it. In other words, it only depends on the bit sequence of the exponent since the last arithmetic overflow of the accumulator. And that's the key to our attack. So let's see how the practical attack works. We have a pretty classical attacker model for a cache attack with an unprivileged spyware running on the victim computer, which is needed for the flush and reload attack to work since we need to share some processor cores. And having an attacker in a man-in-the-middle position may be helpful if we need to gather more information, but it is not actually needed, and our experiment shows that we get more than enough information from only one measurement. So here is the classical attack workflow. We have a legitimate user trying to connect to a service or anything using SRP with their valid password. If we meet our requirements, we have our spy process monitoring the user activity. Hence, when the client computes the verifier during SRP, the spy will generate some execution trace that can be parsed. With this trace parsed, we can extract some relevant information, namely when did the accumulator overflowed and needed to be spilled into the results. And from this information, we are able to perform an offline dictionary attack and remove any password which doesn't meet the criteria defined by the information we recovered. Let's get back to our exponentiation algorithm. We can see in the middle that the actual result, not the processor word, but the big number results, needs to be squared at each iteration to be kept updated. And this is actually nice for the attacker, since spying on this operation, which is longer than a classical word squaring or multiplication, allows us to distinguish one iteration from another. In a classical iteration, without arithmetic overflow of W, the result is only updated once. However, whenever W overflows, the result is updated once more, leading to a longer iteration. We can slow down those iterations even more by applying the performance degradation attack in this piece of code, making the overflowing iteration even more noticeable. With this measurement, we end up with quite nice graphs, where each blue cross under the threshold represents a call to the squaring of the result, hence a new iteration. And every time we get a long pause in between two crosses, we have an overflow of the accumulator. As stated earlier, for a given word size and base, the number of iterations between two overflows only depends on the bit sequence of the exponent. And we can quite easily map the number of iterations between two overflows to the bit pattern in the exponent and define some rules to apply to our trace in order to recover some bit value. Here is the set of rules we end up with for a 64-bit architecture and the base j equal 5, which is the most commonly used base as of today. Here the value b represents an unknown bit, and the 4 y's represent a subset of the possible values for those 4 bits. Notice that if we only get 4 iterations between two overflows, we can guess exactly the value of 3 of those 4 exponent bits. Otherwise, we can only guess part of the bits, but we can still significantly reduce the set of possible values. Now, consider that the trace gives us the following execution flow, where each v is an iteration, and spaces denote overflows of the accumulator. By simply applying the rule to each group of bits independently, we can get a lot of information on this sequence. However, notice that we don't get as much information on the last group of bits since we don't know when the accumulator would have overflowed. Now that we have recovered this sequence, how do we find the password? Remember that the exponent x is defined by the password and two public values. Then the only thing an attacker needs to do is to take the recovered bit sequence and compute the x value corresponding to all password candidates from its dictionary and see which one match the most. Of course, we can't expect a full match since some of the bits are not recovered, but simply counting the differences allows to highlight the most probable password which should have less differences than the other. Now let's discuss why do we need a single measurement to perform a realistic password dictionary attack. First, we have a very accurate measurement by combining the flush and reload and the performance degradation attack in such a way. So there is almost no error and we're able to extract as much information as we could using our rules. So we don't need to repeat our measurements in order to smooth out some errors. The second point is that on average we get a lot of information from a single exponentiation. And even if this information is scattered across the exponent, we can exploit each bit of information independently. This is because the hash function behaves as a random oracle, so for any password, each bit of the corresponding x value has a 50% chance to match the trace we recovered. This means that each bit of information we recover allows us to halve the set of possible passwords. In other words, if we recover k bits of information, a wrong password only has 1/2 to the power k chance to match our trace. And with our rule-based pattern matching algorithm, for n-bit exponent, or still for j equal 5 and a 64-bit architecture, we recover about 0.4 n plus 2 bits of information, meaning that using SHA-1, as it is the case in OpenSSL's implementation of SRP, we get about 66 bits of information. Other implementation, which switch to a more secure hash function such as SHA-256, leaks even more information because the bigger the output of the hash function, the more information we get from our trace. As I said earlier, we spent quite some time finding which project used this implementation. Of course, OpenSSL implementation is vulnerable, but we rarely see TLS SRP being used. However, quite a few other projects used OpenSSL API to provide an SRP implementation. First, we can mention the case of Apple HomeKit ADK, which is a development kit for Apple connected device, where SRP is used to pair your Apple phone, laptop, or tablet to an Apple IoT device using a PIN code. And those IoT devices run from garage door to light bulb or doorbell, so we can think of a lot of issues. It is also the case of PySRP, which is a Python SRP reference package, namely used by ProtonMail's Python client to authenticate the client upon connection. And it may also be the case of GoToAssist, a software for remote support, allowing to share your screen and give control of your computer to an expert. Here, SRP is used to establish the secure session protecting screen sharing, keyboard and mouse control, diagnosis data, and text chat. Thus, an attacker recovering this secret password may be able to put themselves in an active man-in-the-middle position, achieving complete control over the victim computer by impersonating the IT support. For this last one, this still has to be confirmed since their project is closed source, but they clearly reference SRP in their documentation and clearly state that they use OpenSSL for the cryptographic implementation. We contacted them, but they did not respond to our emails. Finding that OpenSSL is being used in this project made us wonder, what about the more generic big number implementation in higher level languages? And it turns out that there is basically two options. Maybe they re-implement it from scratch completely, or maybe they rely on a lower level big number library like OpenSSL. And it turns out that many reference packages for either big number arithmetic or straight cryptographic implementation are basically mapping to OpenSSL, inheriting its vulnerabilities. And they usually don't bother touching the constant time flag, which we can completely understand since they assume that the library is handling those things securely. But this means that not only those packages or library inherit the vulnerability, but all SRP implementation based on those are also vulnerable. And it is hard to know exactly how many projects are impacted, since some of them may be closed source, and even for open source projects, it is not always very easy to know which project is implementing SRP. So we discussed this issue with OpenSSL, of course, and two mitigations came out. First, we could simply add the constant time flag to the implementation of SRP in OpenSSL code. This is very easy to do, but it only patches OpenSSL's SRP implementation, and all other implementation which usually use the big number API rather than the SRP API from OpenSSL will need to be patched independently. A broader patch and more suitable for long-term fix would be to switch to a secure by default approach, namely on such sensitive function. However, the latter proposition was declined by OpenSSL because of a potential performance loss, and OpenSSL chose to apply the first fix, leaving most of the impacted projects vulnerable. So OpenSSL patch being deployed, we contacted all other projects that we found to be vulnerable, and most of which thanked us for our patch and applied it in a very timely manner. However, we mostly identified open source projects, and proprietary software may still be vulnerable, and we may have missed some open source projects. So in a nutshell, we described an attack on SRP implementation which applies to many projects and packages. And this attack is very practical because we could exploit the information of each recovered bit independently and didn't need to recover the full exponent or anything like that. And this shows that even well-audited library in their most critical functionality still have issues and that such channel leaks are very tricky to detect. It also shows us that we need to be extra careful when implementing PAKES, since the smallest issue may lead to a very big attack. And finally, the root cause of this vulnerability is a weak exponentiation algorithm, which may be used in other protocols if the flags are not set carefully and if the base is small enough to fit in a processor world. We couldn't actually think of another protocol which fits this description, but if you find one, feel free to contact us. It could be the beginning of a nice collaboration. Thank you very much for your attention. If you want more detail about our proof of concepts, they are available on this GitLab pages. And if you have any question or if you want to discuss it further, feel free to contact me at this email address. Thank you very much.